Welcome to our paper DERD, Learning Depth from Event-Based Ray Densities. A major goal in robotics is to develop systems capable of autonomous navigation. By accurately estimating the depth of the surrounding objects, robots can build a 3D map of the environment. Traditional cameras combined with AI have been widely used for this task. However, frames suffer from redundant data, motion blur, and limited dynamic range. Event cameras, by contrast, record per pixel brightness changes asynchronously, thereby capturing motion with microsecond resolution and minimal blur. Their high dynamic range and sparse output make them ideal for SLAM in high-speed, high-contrast environments. Yet, applying deep learning to event cameras remains a major challenge, as the data is fundamentally incompatible with conventional neural networks. We introduced DERD, the first event-based multi-view steering method that uses deep learning for 3D reconstruction. Our method takes events over a short period of time as input and back-projects them as rays into space using known camera motion. 3D space is discretized into voxels that count the rays that pass through them. This intermediate geometric representation is called a disparity space image, DSI. Next, we learn depth from the DSIs by processing local subregions, called sub-DSI. Each sub-DSI is fed separately to the neural network, predicting pixel-wise depth. Since the sub-DSIs are very small and independent, they can be processed fully in parallel with an ultralight network consisting of only 70,000 parameters and having a very short inference time of only 0.37 milliseconds. Moreover, the local processing of the DSI reduces the risk of overfitting and allows handling any pixel resolution. To evaluate the performance of our method, we compare it to the state-of-the-art model-based MCMVS approach on the real-world benchmarks MVSEC and DSEC, using cross-validation on all sequences. Our method estimates depth even in regions where ground truth LiDAR is missing due to the field of view. Compared to MCMVS, our method produces more accurate depth with significantly fewer outliers. We also retrained and tested our network on DSIs obtained from a stereo outdoor driving scenario with higher resolution. Note the significantly fewer outliers produced by our method. Additionally, notice that our method predicts depth even in regions beyond the LiDAR range. Again, our method produces more consistent depth than the state-of-the-art. The experiments confirm that our method strongly outperforms all previous approaches, therefore defining a new state-of-the-art. On MVSEC, our method reduces the mean absolute error by 42%. It is also able to reliably predict depth on 3 times as many pixels while reducing the median absolute error by 30%. Remarkably, our method is as good as stereo SOTA using only monocular input. On DSEC, we observe similar and even better performance improvements. Our code, models, and results are publicly available on GitHub. Given our method's exceptional performance, ultra-lightweight architecture, scalability, and flexibility across different configurations, it holds strong potential to become a standard approach to learn depth from events for real-world robotic applications.